Hi, my name is Avril Sauter and welcome to conducting Cisco Unified Wireless Site Survey. In this lesson, we're going to look at the concepts behind doing a site survey. So a Layer 1 site survey is all about assessing the RF environment and then selecting the best channel to deploy your access point on. So we're going to start by talking about interference. What are the different sources of interference that happen in the 2.4 and the 5 gigahertz band, and what's the impact of that on a wireless LAN performance? Once we've done that, we're going to talk about how you can use the Cisco Spectrum Expert tool to identify sources of interference. And so we're going to do an overview of the tool itself and to explain the different RF plots that you can have. We will wrap up with some real-life demonstrations of those plots so you can feel really comfortable with what those plots are actually displaying. So let's start with a discussion about interference. When we're looking at the deployment of wireless LANs, we're looking at deployments in the unlicensed, or what's sometimes referred to as the license-exempt frequency bands, and those are the 2.4 and the 5 gigahertz bands. Now, because they're unlicensed, not only can Wi-Fi operate in these bands, but other devices can also operate in these bands. An example of other devices would be cordless phones, wireless cameras, of course, other wireless LANs other than the one you're deploying. The chart shown on this slide is taken by a tool called Channelizer, where it's just sniffing the RF, and it's actually showing an 802.11gn deployment in the 2.4 gigahertz band, and those are those square-shaped signals that you can see. And you can see that there are wireless LANs deployed on channel 1, 3, 6, and 11. Now, if you look at this diagram, you can also see some yellow spiking that's occurring. That yellow spiking is actually a proprietary wireless system. And what that is that there is a solar power system deployed on this site. And that solar power system captures information about usage and sends it on a regular basis to a controller that's actually in the corporate building. And that traffic is actually what's causing those yellow spikes that you see here. So you sometimes find interference from sources that you don't expect. Now, in general, we say that there's more interference in the 2.4 gigahertz band than the 5 gigahertz band. The reason we say that is that there's been more devices manufactured to operate in the 2.4 than in the 5 gigahertz band. And a few examples of those devices include your Bluetooth, which would be your wireless headset that you use with your cell phone, microwave ovens, and the Zigbee sensoring networks that are often used out in manufacturing and warehouse locations. There are also devices that interfere in the 5 gigahertz band, so it's not uncommon to find cordless phones that operate in the 2.4 and also operate in the 5 gigahertz band. The 5 gigahertz band also has some satellite systems. The radar that is used by the police actually operates on many different frequency bands, but one of the frequency bands it does operate is the 5 gigahertz band. And so you'll also see that, especially in outdoor deployments. Sometimes you'll hear people say you're better off deploying in the 5 gigahertz band than the 2.4 gigahertz band because of the noise that exists in the 2.4 gigahertz band. So I want to explain that to you so you can understand a little bit better. So I've created a chart here where we're going to look at the 2.4 gigahertz band and we're going to compare it with a chart in the 5 gigahertz band. So if we imagine a signal from my access point here in the 2.4 gigahertz band, and you can see the received signal strength is fluctuating up and down because my RF environment is continually changing. If we compare that with the 5 gigahertz band, we know in the 5 gigahertz band that my signal attenuates more, and so my received signal strength will be less. However, if we look at the interference in the 2.4 gigahertz band, and here I've illustrated it, you can see what I care about is my ability to recover the signal above that interference. And so if my interference is less in the 5 gigahertz band, as illustrated here, you can see that my signal-to-noise ratio in the 5 gigahertz band could be equivalent or better than the 2.4 gigahertz band. And so when we look at doing a site survey, what we care about is not only the received signal strength, but what interference do I have there, because it's my signal strength over that interference that allows me to recover your signal, to demodulate and decode your signal and get back to your ones and zeros that you were trying to transmit. Now, when 802.11 was defined, it was defined for deployment in an unlicensed band, and so they knew that other technologies would be operating in that band. And so it was defined to avoid or to coexist with those other technologies. And the way it does that is before it goes to transmit, it'll listen. And it will listen to the spectrum. And only if it hears no noise in that band will it go ahead and transmit. So if there's other technologies that are deploying in that band that device can hear, such as a microwave oven, such as a Bluetooth device, such as a cordless phone, it will not go ahead and transmit. It will wait till that transmission is finished, and once the medium is then free, it will then go ahead and start its transmission procedures. What that means is that if there's interference in the unlicensed band, Wi-Fi will continue to operate, but it will suffer more latency, more delays, because it's waiting for longer periods of time. If it's waiting for longer periods of time, then your overall throughput of your wireless LAN will be deteriorated. So the other impact of interference on your wireless LAN is to impact your modulation and coding. So your modulation is where you represent bits per waveform. So you might use BPSK, which is 1 bit per waveform, QPSK, which is 2 bits per waveform, 16 QAM, which is 4 bits per waveform, or 64 QAM, which is 6 bits per waveform. Now you can only send 6 bits per waveform in good RF conditions, and so if you're suffering interference, what the system's going to do is say, oh, I can't use 64 QAM, I'm going to have to drop back to 16 QAM or even QPSK. If you drop back from sending 6 bits per waveform or 6 bits per modulation symbol down to QPSK, which is 2 bits per waveform, you've reduced your data rate threefold. And so in a noisy environment, when your RF conditions aren't so good, what the wireless LAN will do is it'll drop you back down to lower levels of modulation. It'll add more coding protection. And what that will mean is that your data rate will drop, which of course reduces down your cell throughput as well. So in the last few slides we talked about, hey, in the 5 gigahertz band, my signal-to-noise ratio actually might be better than what it is in the 2.4 gigahertz band. We also talked about how interference can cause me to reduce the throughput of my cell. So therefore, when we look at deployments, there are some advantages of the 5 gigahertz band simply because of the lack of other technologies that's deployed in that band. So the bottom line, as illustrated on this slide, is that when you're deploying technologies in the 5 gigahertz band, you can often achieve higher throughput. And so when we're looking at planning out a voice wireless LAN, Cisco actually recommends that you are able to support 20 simultaneous voice calls if you're deploying the access point in the 5 GHz band, compared with just 14 if you're deploying it in the 2.4 GHz band. Now again, these are what you might expect. The purpose of the site survey is to go out and assess the interference, assess which channels are the best ones to deploy your access point on, so you can make the right estimate as the number of calls that you would expect to be able to deploy in those unlicensed frequency bands. And hopefully, by seeing the tremendous difference in terms of the expected capacity for voice calls between the 2.4 and the 5 GHz band, and this is all, of course, because of the RF environment and of interference, hopefully you'll now understand why doing a predictive model is very useful, but it can never, ever, ever replace the need to actually go out and do a layer 1 site survey and actually assess what the interference is in these bands that you plan to deploy in. So now we want to take